Welcome to the fifth video in section 5.3. What I want to discuss right now is motion on a line. We've got a particle and its position can be described with this cubic for all time greater or equal to 0. And what we want to do is we want to describe the motion. So very quickly, we're going to find the first derivative, which you may remember is velocity. And so the first derivative is, of course, 6t squared minus 28t plus 22. And we want to find the second derivative. And of course, the second derivative of position is acceleration. And so we know that that's 12t minus 28. So now, looking back, what we need to do is find out where each of these is positive, negative, or 0. So we'll start with velocity equal to 0. 6t squared minus 28t plus 22 equals 0. Given that this looks fairly complicated, I could have done some factoring. I could have gotten some numbers out of there. It was easier just to plug it into my calculator using quadratic formula. And what I got was t equals 1 and 3.667, rounding off to 3 decimal places. Secondly, acceleration equal to 0, a little bit easier because it's linear. We know that 12t minus 28 equals 0 at t equals 7/3 or 2.333, again, rounding to 3 decimal places. So I'm going to go to the next page. And if you want to jot those down, go ahead and pause and jot them down. But I'm going to draw my chart on the next page just so that I have room to work and analyze under here. We know that time starts at 0. We know that something happens at 1. We know that something happens at 2.333 or 2 1/3. And we know that something happens at 3.667 or 3 2/3. And it really doesn't matter whether you draw that to scale. So I've just got all my interesting points equally spaced. And so I've got, you know what? I'm not going to do that. I'm going to assume that you can hold the thought in your head that first derivative is velocity and second derivative is acceleration. Because what I've got here is I've got that the velocity is 0 here and here. Again, because it's a quadratic, I know that that graph is going to be positive here, and negative there. The acceleration, the second derivative is 0 right there, and because it's linear, I know that that's going to be negative there and positive there. So what do I see here? Well, immediately I can see that I have a local maximum right here at x equals 1 because the first derivative changes from positive to negative. I have a local minimum right here, and I have an inflection point right here. But what does this mean? What this means is that my particle is moving to the right, and then it moves to the left, and then it moves back to the right again. Notice it moves to the right until it reaches some maximum, local maximum value, and then it moves back to the left for a while until it reaches a local minimum, and then it moves back to the right again. So what this tells me is that at a minimum, I know that because now this goes forever, there is no absolute maximum position. There may be, well, there is an absolute minimum, but I don't know if the absolute minimum is going to be at 0 or at 3.667. I'd have to do some calculations in order to find that. So let's write down what we've got here. Velocity, what do we know? Well, we know that in the interval 0 to 1, the particle is moving right, and it reaches a local maximum at 1 comma, you know what? I didn't calculate these in advance, so I'm not gonna. 1 comma x of 1. We know that from, 0 less than t less than 1, sorry. We know that from 1 to 3.667, the particle is moving left, and it reaches a local min at, 3.667 comma x of 3.667. And we know that for t greater than 3.667, it's moving right. So there is no absolute maximum position. Again, I leave it to you to, if you want to calculate these two, calculate that local minimum. And if it's negative, if it's less than 0, then that's the absolute minimum. But if it's positive, then 0 is the absolute, times 0. Times 0. Oh, let's be careful there, because we have a position. We also have a initial position, which we would have to calculate. So one of those will be an absolute minimum. One of them will be a local minimum. Now let's briefly talk about acceleration. Acceleration, well, looking at this, negative acceleration, because we've defined positive as being to the right, negative acceleration means that this is decelerating. It is being dragged to the left. Positive acceleration means that it is accelerating. What does that tell us? Well, it explains why it moves to the right and then stops and then moves back to the left, because the acceleration is a drag on this particle. As the particle moves to the right, acceleration is pulling it backwards, and eventually it's going to slow down, and come to a full stop. And then it starts moving to the left. And notice that at some point during the leftward movement, the acceleration then starts pulling it back to the right. So the point of this one little section, really to get a feel for what this could mean. What do we mean when we say that we've got a positive slope and a negative slope and a positive slope? What do we mean when we say a negative second derivative or a concave down, or a positive second derivative and concave up? Well, here's a good example of what that looks like in real life. And this is a pretty common problem to see this velocity of a particle problem. So go ahead and do exercise 25. And we will be back in the next video with the second derivative test. All right, thank you for watching.